Hi everyone and welcome to another lecture, and as you can see the title is as linear operators continued. That is, today we are also going to discuss more about linear operators. So let's say first we want to take a look at some properties of linear operators. So let's write them down. So let's call properties. Note that we are not saying the linearity here explicitly, because in the last lecture we discussed about what do we mean by linear operators, and linearity was discussed in the last video. So today we want to take some simple properties that these linear operators have. And the first thing is, if you have two operators, that is x and y, let them be some operators and they're linear, right? Because we are discussing only linear operators. Then you can add these two operators and this will be some operator, let's say z. So if you add two operators you get another operator, and this addition is commutative, that is the order doesn't matter. Similarly, if you have three linear operators as x, y and w, then there is this associativity that is also satisfied by them. That is, first you do y plus z and then you add the x is equivalent to x plus y. I mean, not equivalent, equal to this. So these brackets don't matter. So this is the commutativity of addition, and this is called the associativity. And again, if you work in finite dimensional space, you can always compare these properties with the standard matrix addition. Now let's talk about multiplication, and this is where interesting things will happen. Multiplication. So our linear operators x times y will not always be equal to y times x. This is only possible, so this is the general case, and if this general case is satisfied, we say x, y and the commutator that is given by the multiplication of xy minus yx is not 0. And this, okay, let me just write it down again. We talked about this when we talked with matrices. So this is the commutator. The importance of this non-commutativity lies in the fact that some operators correspond to observables. That is, you can let's say you want to measure the position of a particle, the momentum of a particle, and stuff like that, the energy of a particle, and they always correspond to some operator. In fact, those are known as Hermitian operators, but we'll discuss them in the next lecture hopefully. So let's just take this for granted, that some operators can correspond to some observables, and if they don't commute, that means those two operators when they act on a state will give rise to some uncertainty. That is, you cannot measure the values after those operations simultaneously. So to be more precise, let's state another fact from quantum mechanics, that these states, let's say some n, will correspond to some state. And if you have a state and you have two operators, that is x and y, then x, y, n will not always be equal to y sorry, yxn. And after doing these measurements that corresponds to x and y, that is x and y will correspond to some measurement, x and y correspond to some measurement. If they don't commute, that means you cannot measure them simultaneously. We'll discuss these things in detail when we talk about Hermitian operators and their commutators. So let's just, for now, let's just keep this to a mathematical point of view. And so we defined the commutator, and now we want to define something called an anti-commutator. So the anti-commutator for these two x and y will be given by this curly braces, and this is xy plus yx. So this is our anti-commutator, and they play a significant role when we deal with fermionic oscillators or fermionic variables. In those cases, this anti-commutator is very important, and the fact that these commutators and these anti-commutators are of special interest also lies in the fact called algebra, because you see that we are discussing linear algebra, right? But for that we needed some vector space first, and on those vector space we could do some manipulations. But when you add these commutators or anti-commutators, you are also giving that vector space an extra structure. In fact, a vector space with this antisymmetric product, that is, this is called an antisymmetric product. It's called an antisymmetric product. A vector space where this antisymmetric product is defined will correspond to some Lie algebra, something that you will learn if you take a group theory course or a Lie algebra course. And this is significantly important in the field of group theory, especially for physicists. So these are these extra structures that you can add. And now let's talk about, since we have talked about these properties, what we want to do now is that we want to know can we construct our operators with bras and kets. With bras and kets. The answer is yes. And let's say you have an operator, let's call it A, some operator. You can write it as like this, where beta and alpha are not necessarily the basis vectors, and this product here, it is known as an outer product. And this outer product will give you these operators, and with this definition of this outer product, there lies an important axiom that is called the associative axiom, and Dirac calls this postulate the associative axiom of multiplication. And the importance you will see in a second. Let's say you have this operator A acting on a get. So let's try to do that. This A acts on some get gamma, and we have written this A in terms of this bra beta and this this get beta and this bra alpha, and let's use this here. So let's put a bracket first, and then you write this gamma, right? Now here lies another important piece of our bracket algebra, that is it's P, and this is a bra, this is a ket, so you can sandwich them. If you do that, this will be just alpha, gamma and beta. And recall from inner product that this is just a number. This is just a number or a scalar. So let's just write scalar. This is just a scalar. And what you can do, you can just place it in front of the beta, and that is it. So this will prove very advantageous when you manipulate operators in the bracket notation. And in fact, the elements, like we talked in our previous lecture, that the matrix elements of the operators are basis dependent, and the way to say is from here, this beta and alphas. So if you want to construct this operator, let's say A, in terms of the bases, so what you need to do, you need to just write Aij. This is the ith row and this is the jth column, and you have a sum over these things. And also note that we represent any element of Aij. Let's say I want to know the m and the nth component, that is the mth component, that is the mth row and nth column. So if you do that, instead of here you will have ij, and note that this m and n, they are also bases as well. So if you do that, okay, let me write it in a more clear manner so that you can understand how this algebra works. So you have m over here, here you have a bracket, you have ij, aij, ij, oops, now you can pull out the summation sign because of the properties of the linearity in ket and linearity in bra, and let's just sandwich them. If you do that, this will be aij, here you will have a m, I, and you have a j, n, something like this, right? And finally, what you need to do, you need to use the fact that our bases are orthonormal. So again, you write the summation thing, ij, this is what delta mi, and this is delta jn, and you have two delta functions now and two summations, so you can just get rid of them, that is, you sum over these i's and j's, and the remaining indexes are m and n, and you put m instead of I and you put n instead of j, so this will be just m amn. So these are the advantages that you get from the associative axiom that makes the life a lot easier. That is, if you want to know what are the elements, what is the element in the mth row and the nth column, this is how you go on. And again, I want to go back to the commutator of our linear operator. So let's take two operators now. Let's take omega and lambda to be our linear operators, and it can be shown that, and for that we need another operator called theta. So let's take theta to be another operator, another linear operator, and it can be shown that omega commutator with lambda theta is equals to lambda omega theta and omega lambda theta. And similarly, if you want to have lambda omega theta commutator with theta, you have lambda over here, omega theta. The first term is identical to the previous one, and the second term would be lambda theta, and you have omega. And these two things kind of corresponds to the product rule of the derivative operators, or so to say differentiation. So this corresponds, okay, let's not write corresponds, this is similar. This is similar to the product rule of derivatives for derivatives. In fact, when someone works in the Heisenberg picture, when someone wants to work in the Heisenberg picture, in quantum mechanics, one can see that if this is an operator A, the rate of change of A with respect to time is equivalent or similar to, because the reason I'm giving a similar, because there might be an H and an I, but I'm just ignoring this for now, is equivalent to the commutator of A with the Hamiltonian. So this H corresponds to something called an Hamiltonian operator. And what does this Hamiltonian operator gives us? It gives you the energy of some particle. So this is a nice application when you see in physics. So this commutator, so from this we can say that commutator is similar to taking derivatives. And for today, we finally want to look at the inverse of an operator and how to do dagger operations when we have two or more operators multiplied together. So let's first talk about the inverse of an operator. So there is a very critical theorem that ensures that if you have an operator, whether that operator has an inverse or not, but we will not discuss it here. So let me write a bold assumption, assuming the inverse of operator omega, let's call it omega, exists. We accept it because we are assuming it, right? So I'll just take this assumption, and the inverse will be defined as something like this. So let's say if you have omega and you have omega inverse 1, this is how the inverse is denoted, then it will give you the identity operation. And you can also write it as omega inverse 1 and omega. So this is similar to matrix inverse that you saw in week 1 lecture, that this can be thought of as a right inverse, this can be thought of as a left inverse, and if both of them are the same thing, that only then this inverse exists. But it can be proven in a very abstract manner, it can be proven in a very abstract manner when you can have an inverse or not, but let's not go there today. And this is how you can write this inverse. And if you have, let's say you have a product of operators like A, B, and the inverse will be just B inverse, A inverse, and so on. Similarly, the dagger operation or the adjoint operation is something like you have two operator product, that is A and B, and you want to dagger it. This is like B dagger, A dagger. And with the help of bracket notation, you can easily prove these things. Also, you can switch to index notations and you can do it. And this will be it for today. I hope you enjoyed it, and I'll see you guys on the next lecture. Thank you.